Now, let's move on to another important type of function, rational functions. A rational function has the form p of x over q of x, where both p and q are polynomials. This polynomial represents p of x, and this polynomial represents q of x. In the top polynomial, the leading term is a term with the highest degree, which is an times x to the n. For this polynomial, n is the degree of the polynomial, and an is the leading coefficient. This polynomial represents the denominator. In this polynomial, bm times x to the m is the leading term, and m is the degree of the denominator. bm is the leading coefficient of the denominator. For rational functions, the end behavior depends on the degree of the numerator and the degree of the denominator. Case number 1. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator. So if n equals m, the horizontal asymptote is the ratio of the leading coefficients, which is an over bm. Case 2, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. So if n is less than m, the denominator grows faster, so the whole fraction goes to 0. Case 3, if n is greater than m, then there is no horizontal asymptote. There is a special case if n is 1 larger than m, then the function has a slant asymptote. And to find the slant asymptote, we use the polynomial division. We take p of x divided by q of x, and the quotient g of x is the slant asymptote. Now, let's apply these rules to an example. We're given f of x equals 2x plus 5 over 9x squared minus 11x plus 2. We want to find the limit of f of x as x approaches infinity, the limit of f of x as x approaches negative infinity, and describe the end behavior. This is a rational function. The degree of numerator is 1, and the degree of the denominator is 2. Let's compare the degrees. 1 is less than 2. So the degree of the numerator is less than the degree of the denominator. That means the horizontal asymptote is y equals 0. That means both limits should be 0. Now that we have the answer using the rule we just learned, let's confirm it using the official limit method. We want to find the limit of f of x as x approaches infinity. So first, we need to replace f of x with this fraction. Before solving, notice something important. As x approaches infinity, the numerator becomes very large. The denominator also becomes very large. So we have infinity over infinity. This is called an indeterminate form because we can't just plug in infinity and get an answer. So when you see infinity over infinity in a rational function, we will divide the numerator and denominator by the highest power of the denominator. This is my denominator, and the highest power is x squared. So we divide everything by x squared. So in the numerator, we'll have 2x over x squared plus 5 over x squared. In the denominator, we'll have 9x squared over x squared minus 11x over x squared plus 2 over x squared. Next, we are going to simplify each term. 2x over x squared is 2 over x, and 5 over x squared is 5 over x squared. 9x squared over x squared is 9. 11x over x squared is 11 over x, and 2 over x squared stay the same. Now, as x approaches infinity, 2 over x approaches 0, 5 over x squared approaches 0, 11 over x approaches 0, and 2 over x squared approaches 0. So the expression becomes 0 plus 0 over 9 minus 0 plus 0. And we have 0 over 9, which is 0. Next, to find the limit of f of x as x approaches negative infinity, we replace f of x with this fraction. As x approaches negative infinity, the numerator approaches negative infinity. And as x approaches negative infinity, the denominator approaches positive infinity. So we get negative infinity over infinity. This is an indeterminate form because we can't just plug in negative infinity and get an answer. So we need to divide the numerator and the denominator by the highest power of the denominator. The highest power of the denominator is x squared, so I divide everything by x squared. Two x divided by x squared is 2 over x. 5 divided by x squared is 5 over x squared. 9x squared divided by x squared is 9. 11x divided by x squared is 11 over x. 2 divided by x squared is 2 over x squared. As x approaches negative infinity, 2 over x approaches 0. 5 over x squared approaches 0. 11 over x approaches 0. And 2 over x squared approaches 0. So we have 0 plus 0 over 9 minus 0 plus 0, which is 0 over 9, which is 0. So we confirmed limit of f of x as x approaches infinity equals 0, and limit of f of x as x approaches negative infinity also equals 0. So the horizontal asymptote is y equals 0. So As x approaches infinity, the function approaches 0. And as x approaches negative infinity, the function also approaches 0. That means the graph gets closer and closer to the x-axis. If the question only asks for the horizontal asymptote, you can use the rule to find the answer quickly. But if the question asks to find the limit, like this one, then make sure you show the work using the limit method. That way, you are not just giving the answer, you are showing how the limit is evaluated. Now, let's work through these examples step by step using the limit method. We're given f of x equals 6x to the third minus 2x squared minus 8x over 5 minus 9x minus 3x to the third. We want to find the limit of f of x as x approaches infinity. First, let's replace f of x with this fraction. Notice as x approaches infinity, the numerator approaches infinity, and the denominator approaches negative infinity. This is an indeterminate form. Sometimes you get infinity over infinity. Sometimes you get negative infinity over infinity. Sometimes you get infinity over negative infinity. Whenever the top and bottom both grow without bound, we use the same strategy. We'll divide both numerator and denominator by the highest power of the denominator. The highest power of the denominator is x to the third, so I divide everything by x to the third. Now, to simplify this expression, we'll take each term divided by x to the third. So we have 6x to the third over x to the third minus 2x squared over x to the third minus 8x over x to the third over 5 over x to the third minus 9x over x to the third minus 3x to the third over x to the third. Now, let's simplify each term. 6x to the third divided by x to the third is 6. 2x squared over x to the third is 2 over x. 8x divided by x to the third is 8 over x squared. 5 over x to the third stays the same. 9x over x to the third is 9 over x squared. And 3x to the third over x to the third is 3. As x approaches infinity, all of these fractions go to 0. So we have 6 minus 0 minus 0 over 0 minus 0 minus 3. So we have 6 over negative 3, which is negative 2. So the limit of f of x as x approaches infinity equals negative 2. Question B, we want to find the limit of f of x as x approaches negative infinity. First, let's replace f of x with this fraction. As x approaches negative infinity, we will have the combination of infinity over infinity, which is the indeterminate form. So we will use the same simplifying expression. And as x approaches negative infinity, all of these fractions go to 0. So we have 6 minus 0 minus 0 over 0 minus 0 minus 3, which is 6 over negative 3, which is negative 2. So limit of f of x as x approaches negative infinity equals negative 2. Question C. We need to describe the end behavior. As x approaches infinity, the function approaches negative 2. And as x approaches negative infinity, the function also approaches negative 2. So the graph approaches the horizontal line y equals negative 2. And if the question asks for the horizontal asymptote, that is y equals negative 2. Now, let's look at the next example. We're given f of x equals 8x squared minus 9x plus 11 over 6x plus 7. We want to find the limit of f of x as x approaches infinity. So first, let's replace f of x with this fraction. As x approaches infinity, the numerator approaches infinity, and the denominator also approaches infinity. Again, we have infinity over infinity. This is an indeterminate form. Even if one part goes to negative infinity, we still treat it the same way. We divide the numerator and the denominator by the highest power in the denominator. The highest power in the denominator is x, so we divide everything by x. Next, we need to simplify this expression. Eight x squared divided by x is 8x. 9x divided by x is 9. 11 divided by x is 11 over x. 6x divided by x is 6. 7 divided by x is 7 over x. As x approaches infinity, 8x approaches infinity, 11 over x approaches 0, and 7 over x approaches 0. So, as x approaches infinity, the numerator approaches infinity, the denominator approaches 6, and infinity divided by 6 is infinity. Question B. We want to find the limit of f of x as x approaches negative infinity. So first, let's replace f of x with this fraction. As x approaches negative infinity, we'll have the combination of infinity over negative infinity. This is an indeterminate form, so we use the same simplifying expression. As x approaches negative infinity, ax approaches negative infinity. 11 over x approaches 0. and 7 over x approaches 0. So as x approaches negative infinity, the numerator approaches negative infinity, and the denominator approaches 6. And negative infinity divided by 6 is negative infinity. Question C. I want to describe the end behavior of the function. As x approaches infinity, the function increases without bound. As x approaches negative infinity, the function decreases without bound. So the graph goes up on the right and goes down on the left. So remember, when both numerator and denominator go to infinity, even if one is negative, we treat it as infinity over infinity and use the same strategy. Divide everything by the highest power of x in the denominator.